cross nature. I'll begin with a word of prayer. Dear Father, we thank you for this day. I thank you again for these students. Just ask you to bless our work today, Lord. In your name I pray. Amen. All right, so let me begin with the discriminant. Definition. The discriminant of x1, x2, xn is D, and it's given by the formula, it is the product I less than j of xi minus xj squared. He says the discriminant of a polynomial is the discriminant of the roots of the polynomial. What have I done? You're talking about diffie Q. Oh, okay. All right. Okay. So he points out that the discriminant is a symmetric function in x1 through xn, and therefore it's an element of the the field extended by the symmetric functions that we talked about in the polynomial section before, right? And then proposition 33 says that if the characteristic of the field is not equal to 2, and sigma is a permutation of Sn, which is also in An, that's true if and only if it fixes the square root of the discriminant D. Let me write that down. Proposition 33 for characteristic of the field not equal to 2, sigma in Sn, then sigma is an element of the alternating group if and only if sigma fixes the square root of the discriminant D. All right, so let me go on here. So let's consider f of x equal to x to the n plus a n minus 1, x to the n minus 1, all the way down to a1x plus a naught. All right. And then, excuse me, with roots alpha 1, alpha 2, alpha n. All right. Then the discriminant for this thing is the product, as we just said, I less than j of alpha I minus alpha j quantity squared. He says, so what would you say about, so I guess my initial question for you is, what can we say about inseparable polynomial? Like, what if that would mean that there are two roots, right? It's got a repeated root, it's right, it's got a doubled factor, so So we have like alpha I equal to alpha j for some distinct I and j, right? Which means that the discriminant is what? 0, right? So discriminant equals to 0 apparently has something to do with separable. He says this. He says d equals to 0 if and only if f of x is not separable. He says recall over a perfect field, which we have not discussed much, but that would be the rationals or a finite field. This implies that f of x is reducible, since every irreducible polynomial over a perfect field is separable. So, yeah.
Where is the alpha I equals alpha j come from? Because like I know that if it's that squared, then that's a repeated.
Right. So that's so the roots we're listing the roots possibly, you know, if we had a double root, we'd list 2 of them. So it's not a distinct list of roots. It's just a list of roots for the polynomial. Yeah. But in practice, if the discriminant's non-zero, then I suppose it's a distinct list of roots, right? So, okay, so discriminant is non-zero then for what we're interested in. He says the discriminant is symmetric in the roots of f of x. And what's that mean? It means it's fixed by all the automorphisms of the Galois group f of x. Oh, it's already left my mind. Let's see here. He says the discriminant is symmetric in the roots of f of x, hence is fixed by all the automorphisms of the Galois group. So D is fixed by sigma in the Galois group of the polynomial, right? In other words, sigma of D is equal to D once more. That makes a lot of sense if you just look at the formula and think about how we described automorphisms in the Galois group, right? They take roots to roots. So if you're taking roots to roots, that means that you're just shifting around the terms in the discriminant. You can almost see it, from the formula. But anyway, he says, okay, so then the discriminant can in general be written as a polynomial of the coefficients of f of x. And he says this is by corollary 31. Corollary 31, back a couple pages here, said it has the fundamental theorem of symmetric functions, which is that any symmetric function in variables x1 through xn is a rational function of the elementary symmetric functions. How is that giving us that? Huh. In any event, these are fairly complicated for larger degrees, but we're going to look at the formulas for the discriminant up to like n equals to 4, okay? Now let me get to it then. So look at this. So it's the square root of D. Maybe I should write it up here. Right? All right, so it follows then that the square root of the discriminant is always contained in the splitting field for f of x. So does that make sense? Well, the splitting field has all the roots of the polynomial, right? And the discriminant is built from a product of differences of those roots, squared. So the square root of the discriminant, of course, I mean, excuse me, the discriminant is built from a product of the squares of the differences, right? The square root of the discriminant is literally built from just differences. So I suppose it's also true that D is in the splitting field, but that's less interesting. All right? All right. And then proposition 34, I think this is the end of our general discriminant theory. Proposition 34 says that the Galois group of f of x is a subgroup of an if and only if the discriminant is an element of the field. Well, if the discriminant D and F is the square of an element. All right. So let's look at the specific formulas. Let's get into it. Degree 2. Actually, what am I doing? Degree 2. Why am I forcing myself to work across the board? Duh. So degree 2. Degree 2. So we're looking at x squared plus ax plus b. All right. And so what? Well, we're going to call the roots alpha and beta. What's the discriminant? The discriminant would be, well, there's just alpha and beta, right? So it's alpha minus beta squared. Right? And so then what? He says this can be written as a polynomial in the elementary symmetric functions of the roots. So how do you do that? Let me not look at what he did. Let's just calculate it. This is x minus alpha times x minus beta, right? That's x squared plus ax plus b. So we can figure out, I mean, yes, in general, the approach he's talking about in terms of elementary symmetric functions probably is necessary to see your way through the mess. But here we can just, hand-to-hand combat figure it out, right? What is it? We're trying to figure out what alpha and beta are in terms of a and b. We're trying to trade the roots for the coefficients. Because most of the times we're given a polynomial that's presented in terms of coefficients, not roots, right? So I see that I've got b is equal to alpha beta, and I've got a is equal to minus alpha minus beta. I'm trying to eliminate. Huh. Dang. How do you do that? Solve for alpha. What if beta is 0 though? Yeah. I mean, I'm not saying you couldn't, but then beta be 0. That maybe be separate. Maybe look at beta equals 0 as a separate case or something, perhaps. I'm going to try squaring it. Right. And if I square this, Well, maybe I should multiply A times B. What's that give me? Well, that didn't help either, did it? Good grief. I'm sorry, guys. Oh, me. So you said, I'll follow Bethany's path. Why not? Why
Or
not?
solve for the first one, solve for the one in A instead of dividing by something in B, make that work.
Solve for the, which one? So this,
So replace alpha in the first one with minus beta minus A or something like that.
so say this one. Oh, let's say alpha is equal to, beta minus A. Is that right? Yeah, yeah. So many minuses. And then B is equal to minus beta minus A times beta, I guess, which is equal to minus beta squared minus A beta. Which is quadratic in beta, so we could solve for it. It's really not where I wanted to go with this. Yeah. You didn't know to admit defeat when you're, well, you guys got a lacrosse game to go to, so I'm going to just put this to death here. So he says that you can prove that the discriminant is equal to the first symmetric function squared minus 4 times the second symmetric function, and so that is, goodness, man, I do not. What's that? Oh, that does?
No, well, sorry, I'm just like thinking because that's like what's in the quadratic formula.
Ah.
Because that's like b squared minus 4ac, I think, or something like that.
B squared minus 4ac.
Like it looks the same.
Yeah. Yeah, I think that,
Like I feel like they're connected.
I feel like this is, this would be going better if I had actually given that lecture this semester. Because last time I gave that lecture was a year ago.
A is the spot that like b would be in the quadratic formula, and there's no A,
Right.
it's one.
Yeah, we should, right. Eventually we should find ourselves to the discriminant, like the thing that goes under the square root in the quadratic formula. Oh. But it's not at all obvious to me why, where'd the alpha and the beta go, you know? I'm sorry, guys. There's a jump here for me.
Wait, so the first symmetric one though, before was like x1 plus x2 or something, so that would be like alpha plus beta maybe.
Oh, so that's alpha.
And then it's minus, and then the second one was like multiplying the two, so that would be alpha beta.
Why minus what?
Like A has a minus in front of it, but.
Well, no, that makes sense in the sense that the coefficient of x should be the sum. Oh, okay, I'm an idiot. See, again, like I said, if I'd actually given that lecture this semester, I wouldn't be such an idiot. Look, it's what exactly you're saying. The coefficient of x is the sum of the roots. Well, not quite. There's a minus. So that's why. Oh, but you're saying that, but this is the discriminant being s1 squared minus 4s2. Where's that coming from? My question is, where's this coming from then? I mean, I agree with you that s1 should be alpha, because generically speaking, you took x minus x1, right? Times x minus x2. And you multiplied it out, right? And that gave you x squared minus x1 plus x2, x plus x1, x2. And then the observation was made that that was S1 and that was S2 on two elements, right? Back in the polynomial section. But what I don't get at the moment is why D has to be S1 squared minus 4S2. Is that somehow obvious from other things I'm not seeing?
So you take alpha minus beta, right, and you square it. That's what the determinant is.
Mm-hmm.
Discriminant.
Right.
And so then you multiply that out, and that's alpha squared minus 2 alpha beta plus beta squared, which is then alpha squared plus 2 alpha beta plus beta squared minus 4 alpha beta. S2 is alpha beta, and S1 is alpha plus beta.
So you're saying it's just a straight calculation.
Yes. Yeah, basically, so like, yeah, take the discriminant, which you know to be alpha minus beta squared.
So I just, right, so your point is that this is alpha, well,
So just square alpha minus beta. No, I would say positive alpha.
well, but S1 is supposed to, oh, you're right. Thank you.
So like you can just start, okay, yeah.
Like that.
I guess you could do that too. I was thinking getting to that from the other direction, from what we know the discriminant will have to be.
Ah,
But yeah, that works.
but of course this is also equal to minus a quantity squared minus 4b, I guess. Well, for AB, right? Oh, no. For B. Yeah, for S2 is B. Okay. So then, all right. I'm sorry. Anyway, I'm burying the lead here. The point is, after you sort through this, you see that the discriminant is just the usual thing we already know from algebra, right? So we find that D is equal to, what was it? A squared minus 4b, which if you look at the way the coefficients appear here, is just the usual discriminant, right? I mean, if we just go back to algebra for a second here, quadratic formula says what? X equals what? Minus a plus or minus the square root. If we just assume it works for an arbitrary field, it does. Not characteristic 2, obviously, right? Remember, this was one of our examples. We discussed that the quadratic formula still makes sense over a field of characteristic not equal to 2. This is still a reasonable formula if you sort through the meanings of things. So a squared minus 4ac, but here that's 4b. So like the thing that appears under the square root in the formula for the zeros of a quadratic is exactly this discriminant. So that's what the discriminant is trying to generalize, is it's the piece. All right, so the larger question is, what kind of field do we need to look at in order to find zeros for the polynomial, right? So the general theory says that the splitting field, of course, has the zeros, and it also is going to have this discriminant, I suppose. The square root of the discriminant, rather, will be in the splitting field. If the discriminant's 0, right, then that means that your original field, the base field where the polynomial appears, you've already got the zeros of the polynomial. You don't even need a field extension to solve it, right? But otherwise, the splitting field is attained how? What's the splitting field look like? So if I call K the splitting field, it's just F adjoin the square root of D, right? This serves as a splitting field. Right? I'm assuming, D is not equal to 0 to make it interesting. So if D is not equal to 0, what are the automorphisms? How would you describe automorphisms of what does aut K look like? Yeah? Basically, you just have sigma equal to the identity, right? There's that. But what's the other sigma? Sigma 2, let's say. Sigma 2, acting on square root of D gives you what? Minus square root of D, right? Because that's all that there is to do. So, for a degree, yep.
Is it sigma 2 of minus square root of D, or is it just like equal to minus?
Oh, I'm sorry. I'm doing everything wrong today. Just minus the square root of D, yes. And then extending past that gives us the non-trivial automorphism, right? So the Galois group of f of x in this case, it's just got sigma 1 and sigma 2, right? I mean, up to isomorphism, the Galois group here is just z mod 2, right? Or the cyclic group of order 2, if you like. And of course, that's solvable, right? So we do have a solution in terms of root extensions. In fact, this is what we knew before we started this whole thing. But then, next, cubic. Polynomials of degree 3. Let's look at what that looks like. So, starting with f of x equal to x cubed plus ax squared plus bx plus c. All right. First of all, he makes substitution x equals to y minus a over 3 substitution. That gives us g of y equals to y cubed plus py plus q. I was hoping that was you, Liam. Yeah.
Are all of the polynomials not having a coefficient in front of the first one? Like,
They're
are all of
all.
them?
Yeah, we want to look at monic polynomials because monic polynomials have everything we're interested in. If you put a coefficient in front of the first term, if it's 0, well, then you're not really in that case. If it's non-zero, since we're working over a field, you can divide. And you might as well make it monic to make things simpler. So, this is called a depressed polynomial. So a depressed polynomial is one for which you've sort of done the generalization of the completing the square trick. You've gotten rid of the next to leading term here. As you can see, we got rid of there's no squared term here, right? And why would this have the same splitting field? Why would f of x and g of y have the same splitting field? And by the way, we're just assuming we're over the rationals for the sake of specificity here, guys. Right? I'm going to leave the discussion of finite fields behind us for the moment. Why would this have the same splitting field as f of x? Can you tell me? And also the same discriminant. The discriminant for f and the discriminant of g would also match. So So like if the discriminant for f was, alpha minus beta, alpha minus gamma, beta minus gamma, supposing that my alpha 1 is alpha, my alpha 2 is beta, and my alpha 3 is gamma, right? 3 roots. So that's your discriminant. Well, find squares. Mm-hmm.
And all the roots are in there, then I have subtract that, it's really going to change it.
Right. So if f of alpha is equal to 0, then I agree with you, but let's look at it this way. If f of alpha is equal to 0, then g of what related thing is equal to 0? F of beta equal to 0, g of what is equal to 0? F of gamma equal to 0, g of what is equal to 0? Yeah, I think you're right. I think alpha plus a over 3 will do it. See if we put y equal to I think that's right. Because if y is equal, let's think about it this way. Yes, if y is equal to alpha plus a over 3, that makes x equal to alpha. And these are literally equal with this substitution, okay? I mean, these are the same expression rewritten, x versus y. So, yeah, alpha plus a over 3, beta plus a over 3. And then what you were just telling me a second ago is exactly the thing, because in the splitting field, if the splitting field has alpha, beta, gamma, this has also got alpha plus a over 3, beta plus a over 3, gamma plus a over 3 also in the splitting field, because a over 3 is in the base field. Why is the discriminant the same? Well, the new roots are shifts of the old roots, right? So if you shift both of them and take their difference, the shift cancels out. So they even have the same discriminant. F and G have the same discriminant. Now, I haven't told you what P and Q are yet. Here's what P is. P is 1/3 of 3b minus a squared, and Q is equal to 1/27th 2a cubed minus 9ab plus 27c. All right. So that's P and Q. And he gives the algebra here and ultimately shows that this implies that the discriminant in this case, and this is not obvious, but the discriminant works out to minus 4p cubed minus 4p cubed minus 27q squared. And you're like, well, that's great, but I only want to know about a, b, and c. Well, great. A, b, c here, what's the discriminant in terms of a, b, c? Well, the discriminant in terms of a, b, c is a squared b squared minus 4b cubed minus 4a cubed c minus 27c squared plus 18abc. So when somebody asks you, does this cubic polynomial have a repeated root, you should be like, give me abc, and I'll plug them into D. If it's 0, then yes. So this tests for repeated roots, among other things. in a cubic. So I think you can understand easily why we don't teach this to algebra students, right? Agree? And so, it then goes on to explain the different cases, all right? So basically, the different cases, the Galois group here has at most order 6, right? And depending on the kind of polynomial you're looking at, either the Galois group works out to S3, or it works out to, I think, Z3. I think it could also be, there's, as he has cases A, B, well, yeah, it has cases A and B here. And he ultimately gives a formula called Cardano's formula. He expresses the roots. You can express the solutions in terms of the discriminant if you go on. Those formulas are all given in here. I meant to write them out on a slide to project them. I just didn't get to it. I'm sorry, guys. Curses. Where are those formulas? They must be in here somewhere. I tell you what, I'm going to write the formulas on a slide so we can look at them together. I don't want to try to write them out by hand. It's just too horrible. I did have a slide prepared for you guys. I wanted to show you. So, yep.
Okay. So the discriminant. Never mind.
So the question is whether the square root of that monstrosity is actually in the field already or not. If it is, then I believe, what would that mean? That would mean, I don't know what that means. Anyway, I should talk more about it another day. I don't think I've said everything there is to say yet, so I'll come back to it. But in the time that remains today, I wanted to show you something. If I can find the... So while we're waiting for this to warm up, you guys can come up and get a muffin. I got apple, and I got banana. I will set out a few of each. Banana. 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 Apple. Apple. Apple.
Thank you.
So good.
Mm-hmm.
This is apple. Yeah, that one. Yes. You're gonna need what? Yes. It is like a cup, like a bunch of people got over there.
Doing what?
So this is a PDF that my brother prepared when he taught Galois theory a couple of years ago. And what he does in here is to show you, it's really interesting what he does. He shows how we generalize, how you can generalize the rationalize the denominator trick that we teach everybody in high school algebra to like rationalizing a cubic in the denominator using Galois theory. Let's see how it goes. So you guys know that, what do? We multiply by, well, we switch minuses on the square root. What is that in the perspective? Oh, it's the only laser I got, sorry. So if you think about it, if we use the non-trivial Galois automorphism on the extend root 5 field, right, that sends 5 to minus 5. So you're basically taking the Galois conjugate of the denominator and multiplying by that top and bottom, right? I mean, so he'll show it down here. But he points out that the pattern is really this. You're taking what's given, you're dividing by the norm of A, and you're multiplying it by the rest of A's conjugates. What's the norm of A? The norm of A is defined to be the product of A and then also A under every Galois conjugate. So really, you can think about the norm of A. A definition is just this. Norm of A, it's the product over sigma in the Galois group of sigma of A. That's what the norm of A is. So like the identity's in there, so that gives you A, and then if we're just dealing with a quadratic extension, there's just two things, so it's just A times A conjugate. That's the norm, which is the norm you've seen in like algebraic number theory if you studied that. But the thing that's neat about the norm of A is that it's fixed by the Galois group. Because if you hit the norm of A with an automorphism, then all it's doing is rearranging the product. So it's the same thing. So it's fixed. In other words, if we're working over Q, it's got to be in the fixed subfield. Certainly, the norm is something in Q. So that's why I say it's a norm. In the same sense, we talk about norms in number theory. So here's an example. Again, pretty simple. Simplified B over A. He multiplies by the conjugate of that, which in this case is not complex conjugate. It's Galois conjugate already, right? And of course, if you do that, what happens? Well, you know what happens. It removes the radical in the denominator and puts the norm. Well, the norm happens to be 41 for this. The norm of A here happens to be 41 because it's 2 plus, what is it? It's minus 41 rather. Sorry. Yeah, minus 41. Sorry. Now, seems like he's missing a sign. Let me go on here. All right, so, and he's like, look, it matches the usual. So he uses Maple, which is it's like Mathematica except with good syntax. Now he says, let's compute the inverse of this. 2 plus 3 times the cube root of 2 plus the cube root of 2 squared. Like, how do you bring that out of the denominator? Well, he says, well, the place to look at that is, the splitting field for x cubed minus 2, which we've talked about before, right? Now, this is a very greedy description of it, but these are the roots of that, right? And so he gives labels to these roots. He calls them alpha, and then omega alpha and omega squared alpha. Those are the specific, Cartesian form for the roots. What's the Galois group going to do? The Galois group is S3. We've talked about this before, and it permutes the roots. So there's 6 things in the Galois group. And so he says he wants to look at specifically how to look at the 1 over this thing. And he wants to recreate the magic here using Galois theory. Right? This is just the black box formula from Maple. So here's his AX is, that's, where's my X? Oh, he's defined X already. He says alpha is root X, this is root Y, and this is root Z. So he's labeling the roots X, Y, and Z. And so AX is root squared 3 times that root plus 2. Okay. So now he calculates all 6 conjugates using his code. So what this is that given A, run through the different possible permutations which permute the roots. The identity, 1 goes to 2, 1 goes to 3, 2 goes to 3, 1 goes to 2 goes to 3, 1 goes to 3 goes to 2. These are the different permutations. And when you sort out what that looks like, these are the different, the original element itself, right? And these are all 5 distinct Galois conjugates. built from the symmetric group of order 3 working on this example. And if you multiply these guys all together, you get 900. And if you multiply all of them except for a and divide by the norm of a, that's supposed to be 1 over a. And that works out to this, which of course is exactly what Maple produced as its rationalize that a element to start with. So we can understand how to bring radicals out of square roots by playing with this norm built from the product of all the Galois conjugates and the element itself. It's pretty neat. It's also something that you should not teach to high schoolers, right? Unless they've been very bad and you need to punish them. And even then, that's probably just punishing you, right? Yeah, pretty much. So anyway, thanks guys. You can, oh, I have, you got it?